Okay, here we are again. This time with more operations with radical expressions. We're going to multiply radical expressions, and then we're going to rationalize denominators. We'll first do a little work with, excuse me, we'll first do a little work with radicals, similar to what you've already done. Then we'll go on to rationalizing denominators. Okay. Before I go to the next page, let's just for a moment think about what rational means. Of course, we've talked about this. It's a ratio. So if I had a number like 1/3, that would be a rational number. If I looked at it as a decimal, goes on and on forever, right? That's typical of a rational number that doesn't divide evenly. An irrational number, such as the square root of 3, that's irrational. If that ends up in a denominator, then we have an irrational denominator, and we want to fix that. So square root of 3 in my denominator. How do I fix it? I want a rational denominator. What will happen is the irrational number is going to move in some form to make the numerator irrational. Right now the numerator is rational, the denominator is irrational. We're going to change that around this way. We're going to multiply both the numerator and the denominator by the square root of 3. So this is equivalent to multiplying this fraction by 1. Will not change its value, but it will change its form. Then we'll have the square root of 3 over the square root of 9. The square root of 9 is a rational number because it is equivalent to 3. So we have rationalized the denominator of that fraction. We're going to do a lot more work with that sort of thing coming right up. We're going to practice with some materials that we've, or problems like we've done before. This is equal to, since these are both a square root, we can express them as a quotient underneath the square root. And when we do that, we're able to carry out this division, which we could not do here. Then we get the square root of 4, which we know is equal to 2. Much nicer looking. Now here we have an addition. The thing we have to keep in mind with addition and subtraction is like terms. We cannot add them if they are not like terms. What does that mean? It means that they have the same variables, if they have any variables. The terms have the same power or powers if we have more than one variable. If we have a radical, they have the same root and the same radicand. Well, these have the same root and they have the same radicand. So these are like terms. They both are the square root of 7, and we have 5 of those in the first term and another 6, positive 6 in the next term, which gives us 11 square roots of 7. This one looks pretty difficult, doesn't it? Well, they do have one thing going for them here. We've got both of these are square roots. So if we could figure out how to get the radicands to be the same, we might be able to make some progress here. So I'm going to rewrite this as the first term, which I'm not going to do anything with, and the second term, which I'm hoping to do a lot with. Well, first of all, it's 4 times the square root. And let's see, what could I do with the square root? Are there any perfect squares in here? You bet your life. There's 12 could be expressed as the square root of 4 times the square root of 3. And the square root of x cubed could be expressed as the square root of x squared times the square root of x. Now we know in this case that x must be greater than or equal to 0. We do not have to worry about x being negative, because if it were in this instance, the whole radicand would be negative, which would not be allowed under an even root. Okay, so that would simplify here to the first term, which isn't going to simplify at all. And then the second term, we're adding 4, and the square root of 4 is 2, so it's times. I'm trying to make a little, I don't know why it's being so difficult. Times 2 times the square root of 3 times x. We don't have to worry about it being negative, so don't have to put in the absolute value, times the square root of x. So I keep going with simplifying this thing. I've got 2 square root of 3x plus 4 times 2, which is 8, times x. And now for my 2 factors here, which are both the square root of 2, I can combine those. Square root of 3x. So I did end up with the same radical, the square root of 3x, but there's another problem. I suppose I could write it like this: 2 plus 8x square roots of 3x. You see, my problem here is that the 2 and the 8x now are not like terms. I can't combine them. I guess I was not destined to be able to combine those. Okay, let's do some multiplication. That's what we said we came here to do. We have the square root of 3 being multiplied by this binomial. We're going to distribute the square root of 3 in, so this is equal to square root of 6 plus the square root of 9. And of course we know what the square root of 9 is, so we've got square root of 6 plus 3 as our answer. Let's stop for a minute and think about a real number. What is a real number? We've recently been talking about rational numbers. And we know that the ratio is the key to that. It's a ratio of 2 integers. So rational. The other big category, irrational. Usually we have no trouble recognizing that a rational number, such as 1/3, can be placed on a number line. Let me make my own little number line here. 0 is 1, 2. So for 1/3, where would I place that on my number line? Oh, right about here maybe? Is that about 1/3 of the way? Suppose I had the square root of 3. Now you could try that on your calculator if you don't already know what the square root of 3 is in decimal. I would need to use the decimal approximation in order to be able to place it properly. It would go somewhere in here. So any real number, whether it's rational or irrational, can be placed on a number line. We'll get back to that in a bit. What have I got here? You know this. This is something that I talk about a lot. Yep. And do you remember why I like these so much? No middle term. And that's going to turn out to be very important to us in a few minutes when we try rationalizing a denominator. I'll show you why in these next two examples. When we have conjugates where the first term and the last term are identical, one of them is a sum, one of them is negative. That's how we recognize that we've got conjugates. When we multiply them together, we do not have to worry about the middle terms. Now you could stop right now, pause this, and go ahead and work this out as FOIL to prove it to yourself. We won't have to worry about middle terms, so what are we going to have to worry about? We're going to multiply the square root of 2 times the square root of 2. So that would be the square root of 4. And then we're going to multiply a positive 1 times a negative 1, which will give us negative 1. And that is equal to 2 minus 1, our most wonderful number 1. There it is. No middle term, we loved it. However, if I multiply the square root of 3, here we have another binomial that has radicals in it, times itself, in other words, square it. Oops, square root of 2. What am I going to have? Of course, I'll have the same thing I had up above, where I multiply the first together, I multiply the last together. But what happens when I do the inside times the inside and the outside times the outside? I get the square root of 6, the square root of 6. I add those together, I've got for a middle term 2 the square root of 6. So this is equal to the square root of 9 plus 2 square roots of 6 plus the square root of 4. And I'm not going to leave it as a square root of 9. It was 3 plus 2 square roots of 6 plus 2. With this middle term, I still have a radical. When we start rationalizing, we are not going to want a radical. We're going to have to figure out what to do with a binomial to get rid of the radical. And we know what to do. We certainly do. This is what we do. Because it has no middle terms. So let's get going with that. Rationalize the denominator. Well, this first one's pretty easy for us. We can re-express this as the square root of 1 over the square root of 2. And of course the square root of 1 is easy to handle. This is where we're ready to actually do the rationalization. All that means is that irrational number has to come out of the denominator. We can do it by multiplying it by itself. And in order not to change the value of the fraction overall, we convert this into a fancy one. And it becomes the square root of 2 over the square root of 4, which is equal to the square root of 2 over 2. That would be our answer. This next one, I can start right out, multiplying by a fancy one. Of course, I'm choosing what I'm putting in my numerator and denominator in order to eliminate a radical in the denominator. That'll give me 3 square roots of 5 over the square root of 25, or 5. So both of these, our denominator has been rationalized. What happened to our numerator? It's where the irrational portion went. Number 3, I think this one's a little tricky. Let's see. Let's write something down here. We'll get rid of it in a minute, but if I have the fourth root of 2x, and I want to get rid of that radical, about the only way to do it is to raise this to the fourth power, which I can do by what I have in the denominator right now is the fourth root of 2x. And what power is that at? Well, of course, we don't see any power here, but we know that it must be 1. We just never write it out. So the fourth root of 2x to the fourth power is equal to what we have up here times the fourth root of 2x raised to the third power. So that tells us what we need to multiply here. Here we have to multiply by the fourth root of 2x, and we have to raise that to the third power. Remember our rule of exponents? Let me write out a 1 here, even though we ordinarily wouldn't. We're just doing it to help our understanding. We know if something has the same base, an exponential expression is the same base, that when they get multiplied together, their exponents add, giving us the 4 that we're looking for. Because if we have a power of 4 and a root of 4, those will cancel out. Oops, I need to have this in my numerator as well, don't I? To the third power, let's see if I can squeeze it in here. The fourth root of 2x, and I definitely should write the 4 down. So I'm going to have the fourth root of 2x to the third power in my numerator, and in my denominator, just a minute, I have to erase something. See if I'm any good at this. Oh, I guess I am. Yes, I am very good at this. I can erase the whole thing. How awful. Okay, just a moment. Sorry about that. I'll try that again. I'll try to be a little more selective about what I'm erasing there. Okay. Not much of an expert with this at this moment. Okay, so here we go. This becomes the fourth root. I'll put it down here. Fourth root of 2x to the third power over, now when I have the fourth root raised to the fourth power, what happens? I end up just with 2x. That's my answer. Okay, let's look at number 4. This is a more interesting one because this one has the binomial with a radical in it in your denominator. Very tricky. Very tricky. Rationalizing this means I have to get rid of the square root of 2. If I were to multiply this radical by itself, you know what would happen. We saw it earlier. When you multiply a binomial that has a radical in it, you end up with a radical in your middle term. The only way out of that is to use conjugates like we did here. So that's what we're going to do. We're going to use exactly the same first term. Then we're going to use exactly the same last term. But this one's going to be a difference because it has to be opposite to this. And we put the same thing in the numerator. And then we go ahead and simplify. We end up with 2 times 3 minus the square root of 2 over, what happens, we square this first term, 3 times 3 gives us 9, and then the square root of 2 times negative square root 2 is negative square root of 4, which is, now our numerator never changes here, 2, 3 minus square root of 2 over 9 minus 2, 7. Here's our answer. One more before we go on to the next page. We're going to do exactly the same approach as we used in number 4, conjugates. It's the reason I've been so excited about them. This is one of the reasons. They're so useful. Using a sum because the denominator had a difference. You want to use the opposite sign in the middle. 5 times square root of 3 plus square root of 7 divided by, now we're going to take square root of 3 times square root of 3 gives us a square root of 9, which is 3. Square root of 7 times square root of 7, which is square root of 49, or 7. And of course it's going to be minus 7. So my denominator is going to be a negative number, negative 4. I'm going to choose to put that negative out in front of my expression here, and we'll have 5 square root of 3 plus square root of 7 all over 4. If it was a negative 4, I put my negative out in front. And you might be thinking, well, wouldn't it be nice to combine the 3 and the 7? I agree, it would be nice, but we can't do it because even though they're both square root, this radicand 3 and this radicand 7 are different. They have to be exactly the same radicand. Okay. Factor out a perfect power. Well, what's the power we're interested in here? This is the second root, so we're interested in factoring out a perfect square. It happens to be there's one here. It's 64. 64 goes into 124 exactly 2 times. This is equal to square root of 64 is 8. Square roots of 2. So factoring out a perfect power like 64 is helps us simplify the expression. Oh, you see the problem here, don't you? Here's a radicand 128 and this 18. No way can we add these together. Even though they're both square roots, which is a good thing, unless these radicands are identical, they will not add. We do know, though, that the square root of 128 is 8 square roots of 2, so let's go ahead and put that down and see if that will be useful to us. I think it is, actually, because we can express 18 as the square root of 9 times the square root of 2. We get 3 square roots of 2. And now we've got 8 plus 3 square roots of 2, which is 11 square roots of 2. Nice. Okay. Here we are with 128 again. It turns out that there's something we can do with this. But first we better think. We're trying to find perfect powers. On 1 and 2, we were dealing with square root, so we were interested in things that were squared. In the case of a cube root, the perfect power will be something which is to the 3rd power. Let's just go through a couple of them that we know. 1 to the 3rd power is equal to 1. That's probably not very useful. 2 to the 3rd power is equal to 8. 3 to the 3rd power is equal to 27. And 4 to the 3rd power is equal to 64. How sweet is that? We already know that 64 goes into this evenly. So we can say the 3rd root of 64 times the 3rd root of 2, which is equal to, excuse me, 4 cube root of 2. Beautiful. Let's look at this one. Well, yikes. The only possible thing that might be able to work here would be 2, let's see, 2 squared is 4. 2 to the 3rd power is 8. I'm looking for 64, you understand. 2 to the 4th power is 16. 2 to the 5th power is, that's right, 32. 2 to the 6th power equals 64. So that's not going to help us here, is it? This is needing something to the 8th power. Well, look down here. Here's a little hint I have put in. Put it into rational exponent form. And you remember that if we have something to the square root, we could rewrite it as something to the 1/2, where in your denominator you have the root, and in your numerator you have the power. Okay, we'll try this. We'll say, okay, so we'll use a rational exponent, 64 to the 1/8. We recognize that 64 is the same as 2 to the 6th, so we could write it that way. Instead of writing 64, we'll say 2 to the 6th raised to the 1/8 power, which, because we know how to deal with the power of a power, remember that one, you multiply the exponents. 6, and we could think of it as 6 over 1, couldn't we? Becomes 2 to the 6/8 when we multiply 6 times 1/8. We can simplify the rational exponent, because what is the same as 6/8? 3/4. And then we could say, okay, we're going to say the 4th power of 2 to, excuse me, the 4th root of 2 to the 3rd power, which could also be written as the 4th root of 8. I think that's how I would submit it. Rationalize the denominator. What multiplier will allow the denominator to be rationalized? What multiplier? So we're not going to actually work these out. You're just going to identify with me what we'd use for a multiplier here in each of these. Once you've identified the multiplier, I think you might agree that the rest of it is not that hard. This one, of course, is going to be a binomial. Okay, we'll go back to number 5. What would we use here to rationalize the denominator? Very good. I hear you. Yes, that's right. This one, of course, not so simple, is it? Think about what we have to arrive at in order to get rid of the cube root. We have to have this situation. Right now, we only have the 1st power, and we need to get to the 3rd. So it's got to be the very same radical, but raised to the 2nd power, because with the same base, you can multiply these together and the exponents will add, and then it will give us what we need. So up here we'll have exactly the same radical squared. Here we have a similar situation, don't we? We're going to take the cube root of 4. Woo! 4. Oh! No! Not to the second. I mean, not to the third power. It has to be to the second power, right? Because we know this one is already to the first. Boy, I almost made a big mistake and recorded it for you. Terrible. Okay, so cube root of 4. The second power. What are we going to do here? Oh, please, I hope it's coming to you so quickly. Conjugates. Don't want any middle term, because if I had a middle term, it would have a radical in it. I wouldn't be able to rationalize my denominator. So I'm going to do square root of 5, square root of 2, and this one is subtracting, so for conjugate, I'm going to be adding. That would do it. Let's just review the rules here for simplifying a radical expression. You factor out all the powers of the root. So in the case of taking the square root of 128, we factored all the second powers of a second, we need to write it down, but square root of second root. And that turned out for us to be the square root of 64. And then we had 8 square roots of 2. At that point, there were no more perfect squares under the radical, and we had accomplished that. The root index is as low as possible. I'm going to go back a page here to look at an example we had of that. This root index right here was 8. That was not as low as we could possibly get. And number 4, 4 would be the low as we could possibly get. And the denominator has no radicals. Remember, when you're faced with a binomial and you're trying to rationalize the denominator, you better use conjugates. Otherwise, you'll end up with a middle term that has radicals in it. So, you say, I am so happy that Mrs. Turner has made conjugates a friend of ours. There we go. I think, let me see if we have done it for today. We have! See you tomorrow.